This presentation provides an overview of the approach taken by Team 1-2 Punch in forecasting values from the reduced M3 competition. The method and forecasts will be discussed in greater detail in the consultancy report to follow. However, we shall briefly cover the data processing, visualization, modelling, forecasts, and conclusions drawn from our approach. The 303 datasets of the reduced M3 data were processed using two R scripts. The first of these was used to generate plots and also used in modelling, while the second was used in conjunction with the first to assess possible state space models. The data was read into R as a data frame. It was converted from wide form to long form using the gather function. Example script is displayed for the quarterly data. The contemporary time period was calculated for each observation by subtracting 1 from the observation number, dividing by the frequency, and then adding to the starting time to present time as a decimal year. Each time frequency dataset was then subsetted by category to create 15 new data frames. The data frame was then converted to a list of each series, expressed as a time series object using a for loop. Quarterly financial data has been used as an example here. Each of the 15 data frames were plotted in ggplot, faceted by series. A few interesting plots are included here demonstrating that there is no consistent theme from series to series. Some exhibit a trend while others do not. Some exhibit seasonality, which may take on different forms, while others do not. Some series demonstrate homoscedasticity, while others demonstrate heteroscedasticity, such as series 159 on the left. Series 70 in the lower right corner is almost deterministic, while series 264 just next to it is almost white noise. Some exhibit trend but no seasonality, such as series 274. Some seasonality without trend, such as series 220. Some exhibit both, such as series 153, and some exhibit neither. Some series, such as series 186 and 189, share common seasonality. Some series, such as series 179 to 183, series 59 and 61, and series 52 and 56, seem to be highly correlated. Other series, such as series 184 and 195, seem to be inversely correlated. The competition rules dictated that the dynamic lag models considering intervention analysis could not be used for the calculation of MACE values. In some series, interventions are apparent, and these interventions create abnormal observations and hence larger residuals that may affect normality assumptions. The left column shows 3 series with a pulse intervention where values spike in one period, overcorrect for the next few periods before reverting to the mean trend level. The center column shows 2 series with negative pulse interventions that affect the observations in one period only. However, these observations may be several standard deviations from the expected value, resulting in large residuals. On the right, there are 2 series, one with a step intervention that affects all subsequent observations, plus a possible further intervention in the final observation of the test data. Aside from the interventions, there is minimal trend and no seasonality. The other on the right also has minimal trend and no consistent seasonality, but it exhibits a short, strong pulse generating an observation very far from the expected value. The consultancy report will examine dynamic lag models on these particular series, but not used for the competition results due to the constraints imposed by the competition rules.
The goal in modeling is to search for the best ETS model for each series. By the best model, it means the model with the minimum MACE. Here we adopt the prediction validation procedure, or also known as P-val, in model selections. The P-val procedures have 2 steps. In the first step, for each series, we split the first 95% as the training data to estimate all possible ETS model. Then we use the last 5% to calculate the test MACE. Based on the test means result, we choose the model with the minimum means and we call this the validation model. In the second step, we create a forecast set by holding out the last 10 periods. Say we have 100 time points, we hold the last 10 as a test data and we leave the first 90 to train the model. Note that we have more observations in the test data set compared to the validation set. Then we train the validation models using the trained data set from the forecast set and calculate the testing phase. Therefore, we have two evaluation rules here. In rules number 1, we use the result from the validation set to assess the accuracy of the fitted model. We also penalize the model which shows some non-normal or autocorrelated residual. Rules number 2, we basically repeat rules number 1 using the forecast set. To automate the p-val process, we wrote a function called AutoETS, which depends on the ETS function from the forecast package. This function depends on 3 key inputs. The first is a list of multiple time series. The second is the whole forecast period. In this case, we pick 6, 8, and 18 for the annual, quarterly, and monthly series. The last is the percentage of data to be split for the validations. In this case, we pick 5%. This function is modified based on the p-val function written by Hader. The key difference is that it passes through all possible model specifications allowed by the ETS functions.
MACE values and penalties were calculated on both the validation set and forecast set. In all data types, the MACE values were worse, as indicated by higher values on the forecast set compared to the validation set. This may imply slight overfitting of the data, or it could be due to the small sample size of some series. In each type, the number of non-normal residuals decreased in the forecast set. This improvement in normality and declining goodness of fit makes sense. As the variance of residuals increases, the MACE value will be worse, but the increased variance will increase confidence intervals, meaning residuals are less likely to be outliers. Although the normality of residuals improved, serial correlations did not. This again makes sense, as autocorrelations would exist in the different timeframes of the same series. This autocorrelation would not be expected to change from validation to forecast set. In each type of data, the median MACE is lower than the mean MACE, indicating that the distribution of MACE values is positively skewed. This indicates that most models perform well with low MACE values, while only a few models perform quite poorly, increasing the mean result. These poorly performing models with large residuals may be caused by interventions. Dynamic lag models may thus improve on these poor models.
In conclusion, the ETS methods produce pretty good results. However, there are alternatives that might improve the performance. For example, the interventions effect, where we mentioned before. Second alternative would be the SCL and AutoRMR. We attempted with these methods, but they proved to be too computational intensive. And the next alternative would be linear empirical model, where we can model some series which exhibit the same structures. And there are more sophisticated models such as a combination between the neural network and time series model. And if you notice, most of the time series are straight positive, so that may have some different assumptions of the error terms. And we also can model multiple time series with vector autoregression model, and there's another one called RMAX proposed by the TSA package. That's it. And these are the references that we build the modeling and the data processing script. And thanks for watching. Bye bye.